Hi everyone. In this video I'm going to show you a function that I've created that allows you to create graphics similar to to those found in Introduction to Practice of Statistics. They have this neat graphic showing the sort of long run behavior of coin tossing. And they do that by, they've got a very long series of trials, and they show what the proportion is incrementally as you climb up through. Obviously not for every sample, or you would get just a crazy blur, but let's say you did 1,000,000 coin tosses, and every 100 you decided to take the sample proportion up to that point and plot it in what would kind of look like a time series of what's happening with the proportion as you proceed through all of your trials. Okay, so what I'm going to do is I'm going to go get the function. So I have it somewhere else. Oops. Okay, we're going to just highlight it and drop it into our console here. Okay, so let me just show you how it works. We would call long run prob of. Okay, and first I should mention this is going to do two trials simultaneously for us in different colors, which makes it very fun to look at. Okay, so what are the arguments? A large number, and that's going to be how many trials total. So let's give it 10, 100, 1,000, 10,000. Let's keep it to 100,000 because I want to make sure that it runs relatively quickly. You know what, we'll even just do 10,000. Okay, and how frequently do we want to take the proportion? Let's say we took it every 50. That should be pretty informative, and let's see what we get. Oh, sorry, I forgot about the probability of success, the other point that we need. It doesn't really matter what it is, because as I'll show you in a second, the way I've defined this thing, it's just like a coin toss. It's not, there's, the random variable isn't anything all that exciting. So it doesn't really matter whether you set the proportion at 0.5 or 0.3. We're just looking for wiggle about the expected value. So we'll just call it 0.5, like a good old fair coin toss. And let's see what R gives us. Okay, that looks pretty good. So I've got a line here at 0.5, and the idea is that in the long run, both of these guys should be converging to 0.5. So let's see what would happen if we just did it again. Okay, we get something different, completely different. It's a new simulation, and we see the same sort of thing. Note on the y-axis here, these things are fairly tight in around 0.5. So I mean, this might look like it's very far from the proportion that we're looking for, but in reality, it's within within 1/100th of it. Let's just do one more to hammer the point home. Okay, well, that one looks like it's behaving really nicely. Okay, great. So now what I want to do is just sort of unpack things and show you how I built this function. So looking at the thing, as always, we give our function some sort of informative title that we hope will remind us why we created it when you look back. We say it's a function of, and we give it the arguments. I've said what's our large number, how frequently are we going to sample on it, and what was the probability of success. Okay, so the first thing I want R to do is create these samples for me. So I've called them large sample 1 and large sample 2. These will be different random samples, but they have the same, you tell R to create them the same way, and then R does its magic and makes them. So I've decided to model the coin toss, and there's different ways you can do this, but I'm doing a binomial random variable, a special one, a Bernoulli trial, because big N in the probability function is just 1. There's only one thing you're drawing from, and we're looking for success or failure, a 1 or a 0 on each trial. Okay, and so we're grabbing how many of those? We're grabbing as many as we asked for. So we're just getting this string of 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, blah, 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 drawn given the probability of success that we stipulated. Okay, so we've got these guys. What was I thinking here? Proportions. Okay, so this is, okay, so these guys are pre-output vectors. They're like, once we get R to do something, it's going to be loading the answers it gets into these vectors. So what I'm doing here is I'm anticipating how many slots I need. Large number divided by the sample frequency is the actual number of proportions that we're going to end up plotting for each of these runs, if you will, of the simulation. So I hope that makes sense. Now I do the actual loop. And this is how you, in R, if you want R to do something over and over again, the same operation over and over on a data vector, you use these loops. So I is the sort of counter for this loop. And I is going to range from 1 to the length of proportions, which makes sense, because that's how many things we want to have happen. So I'm saying our first slot, like pretend I was 1, because I is going from 1 to some number, where I is 1, proportions indexed at 1, what I want that to get is the mean of our large sample indexed from 1 to I sample frequency. Okay, so this part could get a little bit confusing, but it's really not that bad. Basically, the proportion that we're after, that we want to load into our proportions vector, is like the mean of some subset of the samples that we've created. Okay, so what subset? Well, okay, suppose we had 100, we were doing 100 total points in our sample, and let's say we wanted to get the sample proportion after each 10 of them. Okay, so we would want to go on our sample from 1 to 1 times 10, from 1 to 10, and then we'd want to go from 1 to 20, right? We don't want to like skip the first 10 when we go grab the second proportion, because we're interested in the long run behavior of what's going on in our sample. So we would get from 1 to 10, and then we would get from 1 to 20, from 1 to 30, and as you can see, you're just indexing the total number of proportions you're looking for on, sorry, I just misspoke. Right. It's like you want the mean from 1 to whatever number times the sample frequency, from 1 to 10, 1 to 20, 1 to 30, 1 to 40. And you're counting up through, as we know, the length of your output. We do that for each vector, and then it's simply a matter of plotting the output vectors that we've created. We'll plot proportion 1 and make it purple for the plotting character. We're just using these dots, and then we're adding in okay, so we're creating the plot just with proportions 1, but what we're really interested in is adding these line structures to it that sort of chart out what's happened on for each of these vectors. So this plot of the raw points is basically going to get like washed out. We don't even care about it. Maybe I don't even need any of this in here, and I could have just said like, but the thing is, lines adds lines to a graphical plot, so you need it to be adding it to something. Okay, and then I simply added a line that is just a horizontal line at our probability of success, so that we can see what these things should be converging to in the long run. I'll go do one more trial of it just for fun. Hopefully I've had the code up here for long enough that you can. Oh, maybe I'll show off a little bit here. Watch this. Par mf row equal, give it a vector 4, 1. So now I can, like, hopefully that was how you do that, right? So I can call long run probabilities 4 times in a row, and hopefully they should all be sitting here waiting for me to look at them. Yes. Okay, and as expected, these guys all look like they're reasonably well behaved over this very large but finite number of trials. Alright, thank you everybody. So thank you for bearing with me on this part of the explanation. I know that wasn't all that hot, but hopefully you all got something out of this anyway.